Hello and welcome back, everybody. Today we are looking at the part two of section 7.3, which is on trig substitution, but day two. But this time we're going to have a focus on something that is completing the square in this case. And here's what I mean by that. Last time we talked about using a trig substitution when we have an identity or when we have a part of an expression that looks like an identity. Just kind of going back over here just so you can see what's happening. You'll notice that the examples that we have in the denominator, we have the square root of 5x squared plus 6. And so we said, oh, that looks kind of like an identity, so we can make a substitution for. Or maybe the one before that, where we have like the square root of, like, say, a sum of square or difference of square. So in short, any time that you have something like, say, the square root of a squared plus x squared, or maybe something like, say, a squared minus x squared, or the square root of x squared minus a squared, you can use some sort of trig substitution. Now, the problem is we don't always have that form, so we're going to have to kind of like be creative about what happens when we don't have that form. So that's what today is going to be about. So let's go ahead and look at this problem over here that we have set up on the right-hand side or on the left-hand side. So in this case, we have the integral of what's in the denominator is the square root of x squared minus 8x minus 9 dx. Unfortunately, as we said, that doesn't look like a sum of square or difference of square. But if you look carefully, we can complete the square, and hence, that's the reason why we have this section, or that's the name of the section over here. So here's what I'm saying. The bottom part, I have x squared minus 8x. Now, if that thing was a plus 16, we're pretty much golden. But unfortunately, we do not have a plus 16. We have a minus 9. So back in algebra, we say, let's go ahead and balance the equation. So then that way we can see what we actually have on the bottom that might be something that we can work with. So looking at the completed square part right here, that is going to give us x minus 4 quantity squared, and then minus 16, negative 16 minus 20 minus 9, that's equal to minus 25. And hey, look at that right there, we have a difference of square. So now what that means is we can actually work with something that we did with yesterday. Okay. So now we're going to go ahead and again look at our two trig identity over here. Which one does it match up to? So I'm going to need something where it's like, say, a variable squared minus 1. So then that means, looks like, let's see. Wow, looks like maybe either case. No, not either case. It has to be this case over here on the second one, because we need to move the 1 over to the other side to make it work. All right, so my inner function is going to be x minus 4. So that tells me that x minus 4 should be replaced with something. That something in this case is going to be the following then. Taking my identity right here, just writing it in a form that I would like to see better. Tangent squared of theta is equal to secant squared of theta minus 1. So now you can see what my substitution is going to be like then, because I want this guy right here to look kind of like this guy that's over here. So I see x minus 4 is going to be equal to secant of theta, right? Secant of theta. But then remember, we also have the 25 over here, so that could be a problem. So then that means that I need to multiply this guy by 5 over here in my equation to compensate for that extra 25 that's on the outside. Okay, let me just go ahead and show you what happens if I make that substitution right here. So we're going to go ahead and box this guy over here first of all. If I square both sides, that's going to give me x minus 4 squared is equal to 25 secant squared of theta, as my substitution. And then now if I have x minus 4 quantity squared minus 25, which is what I have in the denominator, then that's going to give me 25 secant squared of theta minus 25. And right there, that's definitely something that we can work with, because that's 25 times the secant squared minus 1. And that is equal to 25 tangent squared of theta. All right, so it looks like it's good to go. Okay, so now that we have our substitution, we're going to go ahead and take the derivative. So dx is equal to 5 multiplied by secant of theta multiplied by the tangent of theta multiplied by d theta. Okay, Go back to our original equation. Let's go ahead and make that substitution then. The integral, the top part, dx, gets replaced by this whole thing that we just solved for over here. So 5 times the secant of theta times the tangent of theta times d theta, all divided by the bottom part is going to be, remember, the bottom part is supposed to be this thing over here, right? So according to what we said, we can go ahead and make all our replacement, and in the end, it should come out to be 25 times the tangent squared of theta, all inside the square root. But, let's just go ahead and write it so you can see everything, just so that you can, believe me in this case, because I don't want to skip any steps then. So first, we're going to go ahead, let me go ahead and erase that, okay? So let's see, it's going to be the square root of, let's go ahead and start from this form over here in this case, right? So let's see, we're going to have 25 times the secant squared of theta minus the 25 that we had earlier. So now let's see, the top part is stay as is, so 5 multiplied by secant of theta times the tangent of theta times d theta, all divided by the inside of the bottom part. Well, we're going to go ahead and take out the 25 as we said, and then we also have secant of squared of theta minus 1, and then all of that is inside the square root. Now, fortunately for us, we can hopefully see that the 5 and this extracted 5 on the bottom are going to cancel out. The bottom part over here, that is going to be equal to tangent, because remember, the bottom part is this piece over here. So if I write that as tangent of theta, that is going to be nice because that would cancel with the tangent that's on top. So what we have now is just straight up the square root of secant of theta d theta. Okay. Now this one, hopefully you did memorize it. This is going to, if you did not memorize it, you solve for this using integration by parts. The answer for this, the antiderivative, is supposed to be ln of absolute value of secant of theta plus the tangent of theta, and then we have plus c. You could write plus ln of c if you want. Doesn't really matter in this case, so either one should be okay then. Okay. So that is going to be my antiderivative. Now we need to change everything in back in terms of x. So that means we need to get rid of those secant of theta and tangent of theta. So go to my substitution earlier. It was x minus 4 is equal to 5 times the secant of theta. That was my substitution from way at the very top right there. Okay, so I'm just going to bring that down. Okay, and what we're going to do is we're going to go ahead and create that triangle then. So x minus 4 divided by 5 is equal to secant of theta. Okay, so in that triangle, let's go ahead and draw that out. So here is going to be my theta, and secant is supposed to be hypotenuse over adjacent. So that means that x minus 4 is over here, and then adjacent is going to be over here, which is 5. So if I'm going to solve for this missing piece, that is going to be the square root of, let's see, the hypotenuse squared, so that's x minus 4 quantity squared, minus the bottom part squared, so that's going to be 5 squared. And if you notice, this is exactly the same thing as what we had earlier, which is going to be, from the very, very beginning, the x squared minus 8x minus 9 thing. Okay, maybe it's nice to rewrite it so that way you can see that there's a connection there. Okay, now take our integral and, take our antiderivative, and then we're going to go ahead and make a replacement. Let's see, ln of absolute value. If it's secant, well, I'm just going to go ahead and replace it back earlier because this is equal to secant. So that's x minus 4 divided by 5 plus the tangent. Now this is where we're going to have to use the triangle then. So tangent is supposed to be opposite over adjacent. So that means it's going to be the square root of x squared minus 8x minus 9, and then all divided by 5, absolute value, and then plus c. So this right here is going to be our antiderivative then. All right. Okay, let's look at one more example of this, and let's see how this works out. So this time on the bottom, you'll notice that we do have, again, a difference of square, sorry, a completed square situation. And hopefully you guys can kind of see it, but it's like a little bit augmented from the previous one, but it's still hopefully visible. So here, just so that I can write it in a form that looks a little bit more familiar, let's go ahead and rewrite the bottom part so it looks like it's going to be a difference of square. So let's see. Let me go ahead and write on the side 5 plus 4x minus x squared. If I write that as 1 plus 4 plus 4x minus x squared, then that might actually do the trick then. Okay, so 1 minus in parentheses. Let's see. Does that work out in this case? 1 minus in parentheses. So I'm going to go ahead and say minus 4 minus 4x minus x squared. Ooh, that actually does not look that nice, but let's see what happens. So it's 1 minus in parentheses. Let's see, x squared. Oh, sorry, this is supposed to be a plus right here. And I actually don't want that to be a plus. I want that to be a minus. So maybe this tells me that this problem is a little bit bogus in this case. So I might have messed up in this situation, but let's see if we can fix it then. Okay. So on the inside, I would probably want this to be well, I definitely want this to be a plus 4 then in this case. Okay. So then that way I would have x minus 2 quantity squared in the inside. Okay. So if we do have that, then why don't we go ahead and adjust our problem so then that way we can have this in our denominator. This, if we were to multiply it out, that is going to be x squared plus 4x, and then that's going to be minus, and then it's minus 4, and then we have a 1 on the outside. So I do believe that this tells me that this should be a negative 3 over here. So let me just go ahead and correct my embarrassed mistake and change that to a negative 3 then. Okay. And I think that might actually fix the problem. All right. So sorry about that. But anyhow, that is supposed to be what I want. So let's go ahead and make that modification in the denominator. So now in the square root, we are now going to have 1 minus x minus 2 quantity squared, and then we have dx then. Okay. All right. So once again, we're going to go ahead and make our U substitution, or trig substitution in this case. Hey, look at it nicely. That is the x minus 2, which is a perfect substitution in this case, is supposed to be equal to something. So now this time I didn't write the trig identity on the side because I'm hoping by now you memorized which one is which and which one to use. Since it's 1 minus something, I would prefer to be equal to sine, which is then that way I can get cosine then in this case. So x minus 2 is equal to sine of theta, or remember, you can use cosine if you want. I just like using sine because then I don't have to deal with the negative when I take the derivative. So then dx is equal to cosine of theta d theta then. Okay, so let's go ahead and write the integral. The numerator, we have an x minus 2, so that's just directly sine on the top. Then we have in the denominator the square root of 1 minus sine squared theta. And then finally dx, we're going to have cosine of theta d theta. Okay, so we keep cleaning this up. Sine of theta is just as is. The bottom part, that is going to be cosine of theta. And the top part, we also have a cosine of theta, which we said always, every single time, will cancel out something over there. So in this case, it's just going to be the integral of sine of theta and then d theta. Well, that's workable. The antiderivative is going to be negative cosine of theta and then plus c. And if you recall correctly, I do not want theta, I want it in terms of x. So we're going to have to take our substitution and solve for that then. So over here, we're going to go ahead and draw the triangle so you can see again what is our replacement then. So according to our substitution, if I call theta over here, sine is supposed to be the opposite over the hypotenuse. So let me just write that out. Sine of theta, which is supposed to be x minus 2, which I will write as x minus 2 over 1. Opposite is x minus 2. the hypotenuse is going to be 1. So if I solve for the missing side, that's going to be the square root of 1 minus, in parentheses, x minus 2 quantity squared. So that right there is going to be my missing piece. And that, if you remember, is also going to be the same thing as what we have from the very beginning, which is negative 3 plus 4x minus x squared. Okay, so going back now to my substitution, I want to solve for negative cosine. So negative cosine, that is going to be the adjacent over the hypotenuse. So that means it's going to be the square root of square root of negative 3 plus 4x minus x squared. Okay, and then we have plus c then. And that right there should be our antiderivative, right? Yeah, it looks like it. All right, so this tells me that this problem might have been actually solvable if I were to just use a plain old simple u substitution. But in this case, maybe I just took the longer route then, okay? All right, well, thank you so much for watching. I will see you guys next time. Okay, bye-bye.